This lesson is on the kinetic energy that a rotating object has and how work is done to change that kinetic energy. Suppose you have two ice skaters that weigh the same and they're skating towards one another with the same speed on parallel paths. As they pass one another, they link arms and begin to spin in circles. What is the velocity of their center of mass after they link arms? Well, the center of mass of the two skater system after they link arms is going to be 0 meters per second, because before they linked arms, the center of mass of that system, the velocity, was 0, because there was no external force acting, no net external force acting on the two skater system, causing them to accelerate. And so before they link arms, the velocity of the center of mass is 0, and after they link arms, the velocity of the center of mass is 0. Conservation of momentum. But let's look at this in terms of energy. When they were skating towards one another, they both had energy, and energy is a scalar quantity, not a vector, and so their energies can't cancel out. So they had this large amount of kinetic energy before, and now they're no longer moving forward or backwards. So what happened to that initial linear kinetic energy? Well, there's such a thing as rotational kinetic energy. And all of that linear kinetic energy that they had minus a bit of heat from the collision becomes rotational kinetic energy. How does something get rotational kinetic energy? Well, how did something get regular kinetic energy? Work had to be done. So there has to be a force parallel to the displacement, which then would give something rotational kinetic energy. Or in other words, work would be done if you have a force parallel to the displacement. And so, for example, I have a bike wheel and somebody is pulling on the top of the bike wheel. And so the direction of the force is going to be the same direction as the displacement for some bit of angle. And so there's going to be work done on the wheel, and therefore it's going to gain rotational kinetic energy. So this was the linear world. Work was force times distance. What is it going to be in the rotational world? Well, if you think about just, if you have work equals force times distance in the linear world, what is force in the rotational world? Well, it's torque. And what is displacement in the rotational world? Well, it's delta theta. But let's just show how we get that. So in the example of the bike wheel, work equals force times displacement. And so the displacement is going to be the arc length of that wheel, or delta x. And delta x, we know, is r delta theta if we are looking at delta theta in radians. And so work is F delta x, but delta x is r delta theta. Well, F times r, which they would be perpendicular to one another, is going to give me torque. And now I have torque times delta theta. So this is showing you how work in the rotational world is a little bit easier found by taking the torque times the delta theta. So the delta theta through which that torque is being applied. If you were to graphically look at this thing, you could certainly plot theta and torque. And if you were to then find the area under the curve, that would give you the work that was done during that delta theta. So far, up until this lesson, we've looked at kinetic energy, again, just in the linear world. The proper name for that type of kinetic energy is actually translational, because you're translating from one point to another. So translational kinetic energy, when you actually have some sort of displacement, forward, backwards, up or down, that's known as translational kinetic energy. And now we have rotational kinetic energy. And so translational kinetic energy, we're going to put a little t behind it now. So K with a little t is 1/2 mv squared. So the familiar equation we've used before. Now, if you were to predict what the equation for rotational kinetic energy is by just thinking about, well, mass is inertia. And so in the translational world, m. In the rotational world, I. And v is a velocity. And so in the linear world, v, in the rotational world, omega. It's angular velocity. So the rotational kinetic energy is so similar to translational, except it's going to be 1/2 I omega squared, where K, rotational kinetic energy, I, moment of inertia or rotational inertia, and omega is angular velocity. And as a reminder of units, rotational kinetic energy is going to be joules because moment of inertia is kilograms times meters squared, and angular velocity is going to be in radians per second. Suppose I have an object that's sliding. What type of energy does it have? Translational kinetic. Suppose I have an object that's just spinning, like a bike wheel that you've lifted off the ground and spun the wheel. What kind of energy does that have? Rotational, apart from lifting off the ground. And then what kind of energy does a rolling object have? Well, it's moving forward, but it's also rotating, so it has both. So a lot of times when we look at rolling objects, we're going to have to consider both the translational kinetic energy and the rotational kinetic energy. And in physics paradise, we're often going to talk about something called rolling without slipping. Rolling without slipping involves both rotation and translation. In translational motion, all points have the same translational velocity. So look at picture A. This first picture is meant to be something that's simply sliding. So this wheel is not rolling at all, it's just sliding. So the top of the wheel is moving forward at some velocity, the middle of the wheel is moving forward at some velocity, and the bottom of the wheel is moving forward at some velocity. Every point on the wheel is moving in the forward direction at the same velocity. In rotational motion, all points have the same rotational velocity or angular velocity. So now let's look at picture B. Imagine that this object is not moving forward, it's just staying in place, but it's spinning. And so the top of the wheel has some sort of forward velocity. The bottom of the wheel would have some technically backward velocity, and the middle of the wheel would have no velocity. And the top of the velocity, or the velocity at the top is r omega, and the velocity at the bottom is r omega. They have the same angular velocity, they have the same omega, and if you multiply each by r, then they have the same linear velocity, but just in the opposite direction. But again, and rotational velocities does depend on how far away you are from the center, obviously. In the center, it's 0. As you move farther from the center, it gets larger and larger until you get to some max velocity on the edge. If you are rolling without slipping, the key is the point of contact. So look at picture C. The point of contact on the ground, if we're not slipping, has to be 0. So the velocity between the wheel and the ground, if there's no slipping, has to be 0, which means the translational velocity, so let's just look at the bottom 2 points from picture A and B. So we have a velocity to the right and a velocity to the left. So to the right because of the translation, to the left because of the rotation. Put those together, we get our ideal scenario of rolling without slipping. The bottom of the wheel has 0 velocity with respect to the ground. Now the middle of the wheel is moving to the right, so there's some sort of translational velocity to the right, but yet it's not rotating, so it just has velocity to the right equal to v, which would be the speed of, say, the object moving to the right. Whereas at the top, if you're a point at the top of the wheel, the velocity at the top of the wheel is going to be 2v, because not only is the top of the wheel moving to the right, it's also rotating in that same direction at the top. And so it's going to have 2v velocity at the very top of the roll. So let's look at whether mechanical energy is conserved when an object is rolling but not slipping. Let's start with just slipping. So thinking about just something sliding across the floor. We know kinetic energy is not conserved because as it's sliding, there's going to be friction acting on the system, and that friction is going to do work on the system, changing its kinetic energy, right? Some of that energy is going to become heat. And so the frictional force is going to be kinetic because the two surfaces are sliding past one another. And that frictional force is going to do work. And so there is a parallel component of friction to the displacement. The object is displacing to the right, friction is to the left. So we would take the frictional force times displacement times cosine 180, or in other words, negative work done by friction, therefore a loss in mechanical energy. Rolling, however, the total mechanical energy will be conserved. Yes, there's friction, but it's not kinetic. And so that friction is not doing work on the system, taking energy away. Let me show you what I mean with something that's rolling down a ramp. So when an object is rolling down a ramp, is total mechanical energy conserved? And the answer is yes. If it's not slipping, the energy is conserved as mechanical. Friction isn't, there is friction, but again, it's not kinetic friction. And therefore it's not doing work on the system. So here I would have my frictional force, which is always going to be tangent. It's never going to change so that it's staying parallel to the angular displacement. So again, like if I took my hand and spun a wheel, the direction of my force is going to change for the point on the wheel of interest. So it would then move. So like if I look at that point there where it says friction static, if that was my hand, after some angular displacement, it would now be pointing not just up and to the left, but further up and to the left. It would sort of rotate with the object. And so that force would be applied through an angular displacement. The static friction is not being applied through an angular displacement. It's being supplied only at a point of contact, thus exerting a torque. So yes, friction provides torque, which is why it's rotating. If there wasn't any static friction, it wouldn't rotate. But it's not doing any work because once again, that frictional force is always perpendicular to R. There's never a parallel component of that force to the displacement. So we're going to do a lot of conservation of energy things with rolling objects since energy is conserved as mechanical. Common example is a ball rolling down a ramp or a hill. To start, there's going to be gravitational potential energy. And then at the bottom, there's going to be both translational and rotational kinetic energy. Here I have like a pinball machine where I'm going to take that little pin and pull it back. So I'll do work. And then I'll do my starting position when that spring is coiled. And so there's going to be all kinds of elastic potential energy or spring potential energy. And then it's going to collide with the ball. So during that collision, we will lose some of that energy to heat. But what we're going to have is starting with elastic potential energy. After that ball is going to be rolling, so there'll be some rotational kinetic energy. It's going to be moving forward, so it'll have some translational kinetic energy. But because of that collision, there's also going to be some thermal energy generated. Something that's rolling around a loop. Let's say at the bottom of the track is my initial condition. There's some sort of translational kinetic energy and rotational kinetic energy. And at the highest point, still rolling, still going to have both translational and rotational, but it'll have less because there's now going to also be gravitational potential energy. Let's try a sample problem. Given a ramp whose height is 0.12 meters, predict the velocity of a solid sphere at the bottom. Notice I did not give you the mass or the radius of the solid sphere because, as you might remember from the rotational derby, a large solid sphere tied a small solid sphere because it turns out the mass and the velocity of that solid sphere don't matter. Let's try setting it up. So I have an object that's starting at the top of the ramp from rest. And I want to know at the bottom what that velocity, notice I said velocity as in translational velocity. I didn't say angular velocity. What's that translational velocity of the solid sphere at the bottom? So the initial is going to be the top where we're starting from rest and the final is going to be the bottom. So we're starting with gravitational potential energy. That's going to equal the sum of the translational and the rotational. Gravitational potential energy, mgh. Translational, 1/2 mv squared. Rotational, our new equation, 1/2 I omega squared. So this is a solid sphere. So I can look this up, is 2/5 mr squared. And I can relate the angular velocity to the translational velocity. And the angular velocity is v over r, or in other words, v is equal to r omega. So angular v over r And this is going to be, by the way, the velocity of the center of mass of the system, using the ideas of how these two linear and rotational connect. So I rewrite the equation, but I do plug in the 2/5 mr squared and v over r in for omega. And I end up seeing how r squared cancels in the term to the right. And so I have mgh equals 1/2 mv squared plus 1/5 mv squared. And now I'm noticing that m's cancel, or I guess I combine like terms. I combine like terms, 1/2 plus 1/5 is 7/10. And now noticing, yeah, m's canceled. So the r's already canceled. Now the m's have canceled. And I can show you how velocity is 10/7 gh square root. Or in other words, because we started at 0.12 meters, I now know the velocity of that ball. This is the velocity of the center of mass. The velocity of the center of mass of the ball is 1.3 meters per second. Last question. I have two discs with the same radius and mass positioned at the top of an inclined plane. Disc A rolls down, which is trial 1, and disc B slides down, trial 2. Assume frictional effects are negligible aside from allowing disc A to roll without slipping. So in other words, assume that we're not losing mechanical energy from friction. Which one will reach the bottom first? So predict which one you think is going to reach the bottom first, and then let's talk about the answer and why. Did you predict the sliding one? Well, most of our experiences, we always see friction, and so friction takes energy away from the system, and so the sliding one certainly wouldn't. But in the case where friction is not taking energy from the system, the sliding disc will actually make it down the ramp first because they have the same amount of total mechanical energy. But the sliding one, all of that mechanical energy, all of that potential energy becomes translational. And so translational energy then goes along with that final velocity. Whereas the the rolling one starts with the same amount of gravitational potential energy, but because some of that energy is rotational, we have less translational energy. And so the whole thing is going to be moving slower at the bottom. Therefore, it's going to get there last.